Greetings everyone. My name is Dr. K. We're going to be doing today's session together, and basically this topic for everyone is going to be studying any module that involves math. They're going to be either you're doing pre-calculus or you're going to be doing calculus in your module. This topic right here, it's the basis of the module. So basically it's the backbone of the module. So I'll try to go through the concept very slowly so that you can understand, because the following topics they're going to be doing next week, they're dependent on this topic. So I'll try to go as slow as I can. If ever there's any question, please stop me right away so that I can explain that part right away. Remember that I'm here for you. So don't think that you'll try to catch on along the way. If ever there's any point that you don't follow, just write there. Because if you miss a slide that you don't understand, then it might be hard for you to follow up on the coming slides. So we're going to be talking about limits of a function. So the question could be limits. Maybe before we get to the topic, I think you've seen limits before. Like for example, I took this question paper. It's 2018. So from this 2018, normally you guys, there's a question that says calculate f prime from using first principles. And we know that the formula for first principles is your f prime of x is equals to the limit as h approaches 0, whereby you have to take your f of x plus h minus your f of x. And this is all over h. So I believe this looks familiar. Remember that obviously h cannot be 0. So it means you cannot substitute h to be 0. So basically, because now we cannot substitute h to be 0, we look at the points around 0, meaning we look at h approaching 0. That's why we say that h is approaching 0. So basically, these are the limits, and this is the basis of finding a derivative. Remember that derivative, it means gradient. I remember, I think you guys, gradient of a straight line, y is equals to mx plus c, whereby your m is your gradient. So for you to be able to calculate this gradient, I know that normally we use the formula of y2 minus y1 over x2 minus x1. It's still okay, but otherwise that method is limited. You can't always use it. But otherwise, for us to find the derivative, which means gradient, we have to use limits. So limits is much more of a general rule. So that's why we use limits, because limits is a method that you can be able to calculate gradient for any tangent or for any straight line. Because the one of y2 minus y1, it means that you need the points. You need point 1 and point 2 for you to substitute. But otherwise, if you don't have the coordinates, what do you do? So that's why we use limits. So now, like I said, the limits, they arise when you want to calculate or find the equation of a tangent. Remember that a tangent we said is a straight line that touches the graph once. Even if you have a circle, some straight line that touches the graph only once, or if you have you have a parabola and you have some straight line that touches it once, that is what you call a tangent. So now this straight line, if you want to find the equation for it, or you want to find the velocity, remember that velocity is the gradient. Velocity, remember that is changing displacement over changing time. So this is gradient. And for you to calculate gradient, it means that actually you need to calculate your slope. So your slope is your gradient. And like I said, for us to calculate gradient, we need limits. Now, let's talk about the tangent problem. So we want to find the equation of a tangent to a curve to a specific point. Remember that we said a tangent is a straight line that touches the graph only once. If you have a straight line and it touches only once, so this is the specific point that I'm referring to here. So now, remember that the word tangent, it comes from Latin, the word is pronounced tangens, which means touching. So because we are touching only once. So this tangent of a curve, it touches the curve only at that specific point. I mean, it's up to you which point you want to refer to. I mean, you could have a parabola like that, it could be touching there, or your straight line could be touching some point somewhere there. So whatever point that you referring to, whereby the tangent will be touching the graph at that specific point. But otherwise the point is the tangent touches the graph only once. And again, the tangent should always have the same direction as the curve, because if it doesn't have the same direction, it means that now the tangent will now get to intersect with the function again. Remember that the tangent has to touch a function only once. So it means that if it touches only once, if it doesn't have the same direction, it means that it will touch the graph again. So now, maybe let's take an example. So we want to find the equation of a tangent line to the parabola y is equals to x squared, and we're given a point here. So now, remember that the equation of a tangent is y is equals to mx plus c. So basically, it means that now we need to find our gradient. And as you can see, we've been only given one point here. So we don't have another point for us to calculate the gradient. So it means that now we need to use the limits. So this is there's the parabola, and this rough estimation of how the tangent could look like, because this point that we're given here, 0.11, here it is. So it means that our tangent is touching this point, touching the graph at this specific point here. So this is the tangent. But as you can see, we don't know any other coordinate along this straight line. You can't say this is the point will be here, because remember that this is an estimation. I mean, the tangent line could be looking something like that, or could be looking something like that. So you can't say that there's another point because you're looking at the red line. The red line is just a specific, it's just an example or an estimation of how our tangent line will look like. But otherwise, we don't know the slope of this tangent line. All we know about this tangent line, this straight line, is that it touches this point 1, 1. That's all that we know. So we don't have another point for us to calculate the gradient. So graphically, we can be able to approximate like we just did. I just gave 3 lines that could be possible tangents at this point 1, 1. But now all those are approximate. So we don't know specifically. So for that, they can't give us an accurate solution of how does our gradient looks like. Our tangent looks like. So for that, we're going to use an algebraic approach, meaning we're going to try to calculate the gradient using the limits. So remember that for you to calculate, you either need 2 points, of which you don't have, or you have to calculate the slope of the line and a single point. And this is the approach that we're going to be using here, because you don't have the 2 points. So for that, remember that for you to calculate a gradient, if you have 2 points, or you have 0.1 and 0.2, then this is the normal way that we normally calculate our gradient. So you want to use this approach, but then we don't have the second point. But now, for our second point, what we're going to do, we're going to say that let's Q be some point in the graph, and that point, remember that any coordinate has XY. But now our tangent that we're given here, we're given y is equals to x squared. So we're going to say the y is equals to x squared. So it means that now the coordinates of this q will be x and x squared. And so now we want this q to be close to this point, so that we can be able to have 2 points, so they can be able to substitute that back here, so they can be able to calculate our gradient. I hope that makes sense. So it means that now, remember that if this becomes our, if maybe let's say this is our x1, y1, and this, it means that this becomes now our this becomes our x2, y2, so that it can be able to substitute in this equation. So our y2, as you can see, it will be x squared. So it means that here we're going to be having x squared minus our y1 is 1. So x squared minus 1. And in the denominator, our x2 is just x. And our x1 is just 1 again. So it means that now our gradient, it becomes x squared minus 1 all over x minus 1. So this is our gradient. It depended on some x. So basically, remember that we want this q to be closer to p, because if the q is far away from p, our straight line is not a tangent now, it becomes just a secant. Remember that a secant basically is a line that touches the graph more than once. So it intercepts the graph more than once. So basically this is a secant. Remember we said tangent only touches the graph only once. Yeah, something like that. It touches the graph only once. But if it touches the graph more than once, then we get to call that a secant. So as you can see, we took some point Q along the graph. So you want this Q to be closer to P. So it means that we need to move this point along the graph so that it can, as you can see there, now it moves, we move it closer and closer to the point P. As you can see, looking at here, it's still a second, but then for it to be a tangent, it means that we still need to move this point even further. So it means that we need to move X closer to 1, and yeah. So even this Y coordinate also needs to be moved closer to 1. And again, this point Q, I mean, we said is somewhere along the curve, so it could be on the left of the function. So it could be on the left of the point 1, 1. So for that, it means this, the point Q here it is. So as you can see, this is a second, we want it to be a tangent. Remember we said a tangent, it has to touch the graph only once, not more than twice. So it means that we need to move this point Q along the function so that it becomes closer to the point so that it can just look like a tangent. So as you can see, we move the point Q, still a second, we move it closer. So basically we're moving this X so that it's closer to 1. The X coordinate here closer to 1. So that, as you can see, we moved it closer, and now is when its origin. It's still a second because it intersects the function more than once. So it means that we still need to move this point further so that we have a tangent that touches the graph only once, because that is what we're looking for. So for that, it means that now we want, remember that from here we said we're moving this X values closer to 1. So meaning this X value of this coordinate P, so this coordinate Q is more than 1. So you want to reduce these X values because they are more than 1, want to reduce them to be closer to 1. If you look at these values, the X values here, they are less than 1. As you can see here, we have -3, here we have -2, here we have -1, here it's 0. So we're moving these values which is less than 1. Remember that we want the X values to be closer to 1. So these values from when Q is on the left, these values are less than 1. So we want to push them closer to 1 and see actually substitute. Remember that we said our gradient, remember we're calculating gradient here. Remember we said our gradient is X squared minus 1 all over X minus 1. So we're going to be substituting these X values which are greater than 1. These ones are greater than 1. So we're going to use the X values and keep on reducing them as they get closer to 1 and see how does the formula react, or what value of M of the gradient do we get. And for these values that are less than 1, we're going to substitute the X values, getting closer and closer to 1 and getting to see what value we get for M. So I drew a table here. When you take the values that are on the left, meaning they are less than 1. When you take X to be on the origin, on X is 0, 0.5. When X gets closer to be 1, when substituting from our gradient, remember that our gradient we said is X squared minus 1 all over X minus 1. So as you substitute these X values, this is the value of the gradient that we get. So you can see that here, when the X is approaching 1 from the left, the values of the gradient are approaching 2. And again, when you look at the values of X coming from the right, meaning the X values that are greater than 1, when it starting from 2, reducing to 1.5 as they get to approach 1, we don't really care at 1. We don't really want the X value to be 1 because you can see, as you can see from the formula of the gradient, X being 1, we get undefined. So we cannot substitute the point 1 because it means that we have the same point. So that will be undefined. Remember that we want another point along the curve that is closer to P so that you can be able to have a tangent. And that is the whole idea that we're trying to do. So if you look at the X values that are on the right, reducing them to get to 1, the values of gradient as well, they are also reducing and getting closer to 2. So from this table, we can conclude that actually it means that the tangent of the straight line from the parabola, the tangent to the point 1, 1, the gradient is 2, because we see that from the table that we just drew here. So it means that as the X values approaches 1 from the left and also from the right, the gradient it gets to approach 2, or the gradient is equals to 2. So for that, we get to say that the slope of the tangent line, because the slope of that, remember the slope, we spoke about the secant lines. So we can say that this tangent line, which is 2, it means that now the limit of the slopes of these secant lines, the secant lines, they're approaching 2, which is the tangent line. Or you can say that when you take the point Q, which is approaching P, the gradient between P and MQ, they're approaching M, which is 2 in this particular instance. So when you take the point Q, which is along the curve, and it gets to approach 1, so the limit as Q approaches P, then our gradient between point P and Q becomes M. But now if you don't want to talk about P and Q, we're going to talk about the function itself. We can say that the limit as x approaches 1 of x squared minus 1 all over x squared minus 1 all over x minus 1 is equals to 2. So it means that now our gradient of the function as x approaches 1, the gradient of that function of the tangent line is approaching 2. I hope that makes sense. So basically we use the point slope. So if you want the equation of the tangent, remember that the equation of the tangent can be y minus y1 is equals to m then x minus x1. I hope you are familiar with this equation. We call this a point slope form. So y1, x1, we said there's 0.11 that comes from this point P. We all calculated our gradient. So substituting and simplifying, now we get the equation of the tangent line to the parabola y is equals to x squared. This is the equation of the tangent to the function y is equals to x squared at the point 11. I hope that makes sense. So now we can be able to calculate our gradient. Remember that we only had this point 11. We didn't have another point. But now we managed to calculate the equation of the gradient. Sorry, the equation of the tangent. Remember, like I said, if ever there's any question, please ask me right away before we get deeper and deeper. So now the question is, so I think now we have the idea of what limits are, or what exactly we're talking when you speak about limits. So the question could still remain, what are limits? So now let's get to the definition, because we just gave an example. So intuitive definition of a limit. So basically the idea of the definition of a limit, we can that suppose that you have some function f of x. Now we want to generalize. So suppose you have some f of x, which is defined near a. When I say defined near a, basically what I mean is that f of x is defined on some open interval, meaning if ever your a is somewhere here, we're looking at the points around a. We don't really care about what happens at a itself. We don't care at a's point. Otherwise, we're just looking at the points around a, some interval which around a. For example, in the last example, our interval, remember that we're looking at point 1. And we looked at from 2 and from 0. So we started now looking at the x values from 0 approaching 1, and we also looked at the values of x from 2 approaching 1. So we didn't really care what happens at 1, but we wanted to see what happens around 1. So this is what we mean when you say x near a. So if this function is defined, when you say defined, you mean that for any x value that in this interval we substitute in the function, we can be able to get the corresponding y value. So that's what we mean by defined. So we write the limit of f of x as x approaches a is equals to L. So we say the limit of f of x as x approaches a is equals to L, meaning in the previous example, the limit of our slope as x approaches 1 was equals to 2. So our L was 2 in the previous example, and our f of x, it was the gradient, which was x squared minus 1 all over x minus 1. So this is basically the idea of the definition of a limit. Or we can make the values of f of x close to L, meaning the y values along the function, we get to close the value L as we like by taking the x to be very close, sufficiently close to the point A, either from either side, coming from the left or coming from the right. But we don't really care what happens at A. This is very important. For the limits, we don't necessarily care what happens at A. We want to understand what happens around A. When you get closer to A, what happens? I hope that makes sense. So we could say that roughly speaking, we're saying that the value of f of x, they tend to get closer and closer to the number L, right? As x gets closer and closer to the number A from the left and from the right. And we get to see how does f of x gets closer to L. So, but otherwise, we don't really care what happens at x equals to A. So even if x equals to A gives us undefined, we don't really care. We don't want x equals to A. We want x around A. I hope I'm making sense. So basically, more of this now when you get to precise definition, because remember this definition that I just gave is just intuitive. It's just basically just giving an idea of what we're talking about. But otherwise, getting the precise definition, next week on Tuesday, the lesson there should be focusing on that precise definition. So that we can be able to calculate limits without having to go through all this formula of looking at the x values approaching A and all that. So this is alternative notation of this. We can say that x approaches L as x is approaching A. So this is one way of saying it. Let's take an example. So you want to evaluate the limit as x approaches 1 when for the function x minus 1 over x squared minus 1. So you want to now evaluate this limit. So remember that we said we're looking at the points around 1. We don't really care at 1 because at 1, as you can see from here, if we substitute 1, in the denominator we'll end up 1 squared is 1. So in the denominator we end up having 1 minus 1, which is 0. So that is undefined. So hence we say that we don't care what happens at 1, but we want the values around 1. Meaning the values that are less than 1 and the values that are greater than 1, and all of them keep on reducing them or increasing them, getting closer and closer to 1. So if we take, if we look at this table, we're looking at the values of x that are less than 1. Say we start from 0.5, then 0.9, increasing these values so that it's approaching 1. We don't want x is equals to 1. We just want to see what happens when x is get closer to 1. So as you can see, as we get increase, as you can see the values of the function, they get closer and closer to 0.5. And again, if you look at the values of x that are greater than 1, if you start at 1.5, keep on increasing, approaching 1, the gradient here, it keeps on increasing, and as you can see, it's also approaching 0.5. So because of this, we can conclude that actually the limit as x approaches 1 of x minus 1 over x squared minus 1 is equal to half, based on this calculations. Because even if we take maybe another value of x, you can take 0.99999, yeah. As you can take this value, which gets closer and closer to 1. Remember I said, we don't care what happens at 1. We want to see what happens when we get closer to 1. So it means that even when we take these x values getting more and closer to 1, the more this x minus 1 over x squared minus 1 get closer and closer to 0.5. So for that, because that's what we see on these calculations, we can say that now the limit as x approaches 1 of x minus 1 over x squared minus 1 is equals to half. Remember that half is 0.5, of which this is what we get from our calculations here. So this is how the function looks like. As you can see, remember that this hole here, or this Molanyana circle here, is to say that the function does not exist when x is 1. Because if you substitute 1 here, we end up 1 squared, which is 1, 1 minus 1, it's 0. So we end up having 0 in the denominator, which is undefined. So that's why here you see this open circle here to say that the function is not defined when x is 1. But otherwise, the function f of x, this is how it looks like. So as you can see from the function, when you take the values of x approaching 1 from the left and also from the right, the function here, as you can see, the y values are also decreasing, they're approaching 0.5. And when you come from the right, the y values are increasing, they're getting closer and closer to 0.5. So as you can see, the function get closer to this function here. The function is not defined at 1, but otherwise, when you look at the x values approaching 1 from the left, the y values are decreasing, getting closer to 0.5. And when you come from the right, when you substitute the x values that are approaching 1, the y values are increasing and getting closer to 0.5. So basically, there's the idea of limits. Please know that, remember that as much as this function is not defined at 1, it still doesn't take that actually the limit is equals to 1. It's still true that actually this limit is approaching 1. I hope I'm making sense. Sorry, this would be 0.5. The function is not defined at 1, but otherwise, even though the function is not defined at 1, but as the limit x approaches 1 of this function here, it approaches 0.5. So the limit is defined, but the function is not defined at 1. But the limit approaching 1 is defined. I hope that makes sense. The reason for the limit to exist, because when you find the limit, we're looking at f of x when x is approaching 1. So basically, we want to look at how f of x behaves. We're not looking at 1 particularly, we're looking at the values of x approaching 1. So what matters is how the x values behave, or how does the function behave for the f values defined around 1. So we don't really care what happens at 1, but looking at the values of x when approaching 1 and how the function behaves around that point. Maybe let's try a different example. We use the very same, but otherwise, remember that for the previous example, the function was not defined at 1. So here now we're defining the function at 1. We're saying that when x is 1, the function is 2. Such function, we call it a piecewise. Piecewise function, meaning the function is defined on different domains, meaning on a certain domain, for certain x values, the function gets to be defined by a certain function. And as you can see, when x is 1, the function is defined by 2. When x is not equals to 1, meaning from -infinity until 1, and union from 1 to infinity. So meaning on this domain, or when you look at these x values, the function will be behaving with x minus 1 over x squared minus 1. But when x is 1, remember that these brackets, the round brackets here, meaning we're not including 1. If we wanted to include 1, we'll be using the square brackets. The square brackets are the ones who say that that 1 is included in that interval. But because now we use the round bracket, it means that we're not looking at 1. So when x is equals to 1, we define the function, the y value will be 2. So now we want to look at now this function, look at the limit here. So this is how the function looks like. As you can see, it looks like the previous example, the f of x, but now f of x was just not defined at 1. But in this particular case, this function is defined at 1, and we say at 1, the function is equals to 2. But otherwise, even from this, it doesn't matter. Remember that we said we do not care what happens at 1. We only looking at when the x values are approaching 1 from the left and from the right, and the limit is still approaching 0.5. So we don't care. So even if the function is defined at 1, is given by 2, that doesn't change our limits. I hope I'm making sense. So our limit is still 0.5, even though the function is 2, the function being defined at 1 being 2, it doesn't take away that the limit of this function g is 1 over 2. Because as you can see, as x approaches 1, the y values are increasing, they're approaching 0.5. And when you look at the x values going to 1, the y values are decreasing, they are both approaching 0.5. So meaning the limit is 0.5, even though the function is defined at 1. Let's look at this function here. So we have another piecewise function, and we say that when x is not equals to 2, the function is defined by the straight line, x is equals to 1. And when x is equals to 2, the y value will be 1. So we are asked to sketch this function and also find the limit of g of x when x goes to 2. So what happens with the y values when x values are approaching 2? This, as you can see, the function, you say that, remember that the domain here is from -infinity until 2, union from 2 to infinity. So we say that on this domain, the function will be defined by this straight line x plus 3. As you can see, this is the straight line. But remember that here we said it's not defined at 2, but at 2, the function is 1. So that's why we have this dot here. The y value is 1 when x is 2. So meaning this is the g of x that we are given here. So now, looking at this part, now we want to calculate the limit. What happens when x is approaching 2? So remember that x being 2 here, so we want to look at the values when x is approaching 2 from the left and from the right. And we want to see actually the y values, what will be happening to the y values. So as you can see from here, the y values are increasing. They're approaching 5. Coming from the left, coming from the right, for looking at the x values that are greater than 2, meaning we are this part of the function. The y values are decreasing, they are also approaching 5. So for that, you can just say that the limit of g of x as x approaches 2 is equal to 5. Because as the x values approach, remember we said we don't care what happens at 2. We want to look at what happens when the x values are approaching 2. Looking at the function here, the function keeps on increasing, meaning the y values are increasing. So we don't care what happens at 2, so the y values are approaching 5. And when you're coming from the right, when the x values are approaching 2, the function is decreasing. And the y values are also decreasing. And these y values, they're approaching 5. So for that, we can say that actually the limit of g of x as x approaches 2 is equal to 5. Or the y values of this g of x as x approaches 2, the y values, they are approaching 5. I hope that makes sense. Okay, so now we have this function here. We're evaluating the limits again. We are asked to estimate the value of the limit as x approaches 2 of sine x all over x. So as you can see, we cannot substitute the value of x being 0 here because we end up here having 0 in the denominator, which is undefined. But like I said, when you evaluate the limits, we don't care what happens at this point here. When x is 0, we don't care what happens at 0. We just want to see what happens. How does this function here, how does the function behave for x values around 0? So if you look at substituting the values of x around 0, meaning if you take the positive ones, meaning from the right, decrease them to approach 0, and also take the negative values, meaning from -1, -0.5, approaching 0. These are the y values that we get from the function. This is what we get from sine x over x. So as you can see, these values, they're approaching 1. The function is not defined when x is 0. But when we look at these x values approaching 1, coming from the right, also coming from the left, we get these y values increasing and also approaching 1. And for that, we can say that the limit of sine x over x as x approaches 0 is equal to 1. Because of our calculation in the previous slide. As you can see from this function here, the function is not defined when x is 0, but looking at this function, when x is approaching 0 from the left and also from the right, the y values, they are increasing, the y values are increasing and approaching 1. So as much as though the function is not defined at 0, but the limit is equals to 1. I hope that makes sense. Let's take almost a similar example. We are now asked to investigate the limit of pi over x. Remember, you did the radiant measure in the previous lesson when you guys did complex numbers, and we said pi radians. This is the measure of angles because we normally use 2 degrees. So pi radians is equals to 180 degrees. So by that, I mean, we already know that sine 180, sine 180 degrees is equals to 0. Because remember the function of sine looks like that. So this is at 90 and this is at 180. So for that, it means actually if you use the radians measure, it means that sine pi will also give you 0. If you look at your calculators, normally on your screen, there's a small writing that normally will write DEG to say that you are using degrees. there's also the smalanyana rating written RAD. So the RAD means that now you're using the radian measure. Because if you don't change your setting of a calculator from degrees to radians, if it's in degrees and you type sine pi, it will not give you 0, because in that case you're using the degrees measure. But if you change the setting of the calculator to radians, if you press sine pi, it will give you 0. Okay, enough about that. So we said that we want to investigate this limit here. So investigating this limit, we look at this function, and as you can see, it's not defined when x is 0. But remember, we said for limits, we do not care for x being 0, or when we only interested in x approaching 0. But otherwise, if we take x to be 1, so we end up with pi over 1, so we end up with sine pi. Remember, we said sine pi will be 0 because it's in radian measure. If x is 0.5, meaning it's 1 over 2, we end up with 2 pi, we get 0. If it's x is 1 over 3, 1 over 4, as you can see, if it's actually these x values, this we get all these zeros. But now, don't make a mistake and say that actually it means that the limit will become 0 as if we get to approach 0, the function will be approaching 0. That is, on that, you will be tempted to guess that, okay, because now you're getting all these zeros, taking x from 1, x approaching 0, decreasing x values, and you're getting all these zeros, therefore wanting to conclude that the limit of sine pi over x as x approaches 0 is 0. That will not be true. That is not true, because if you take x to be 0.6 recurring, or 2 over 3, if you take your x to be 2 over 3, then substituting into that function, you get 1. So it doesn't mean that all the x values that you substitute will give you 0. As you can see, if you take x to be 0.4 or to be 2 over 5, you get 1 as well. Sorry. So this is how the function looks like. But now remember that here we are investigating on actually what happens when x is approaching 0. But now remember that 0 is here. So as you can see, when the function is approaching 0, the function is oscillating between -1 and 1. So the function does not get to a specific value as we get closer and closer, because if you look at the previous example, when x was getting closer to 1 or getting closer to 2, the y values, both from the left and from the right, the y values will be approaching a certain specific point. But in this specific example, because if you look at the x values approaching 0 from the left, the function keeps on going up and down between -1 and 1. And also if you look at the x values approaching 0 from the left, the function keeps oscillating between 0 and 1. So the function does not go to a specific value. And for that, because the function is oscillating between 1 and -1 infinitely, as we get to approach 0, then for that, that's why we say that the limit does not exist, because the y values are not getting to a specific value. So since f does not approach a specific point, as we look at the x values approaching 0, therefore the limit of sine pi over x as x approaches 0, that limit does not exist. I hope I'm making sense. I'm going to keep on continuing. If ever you have a question, please hit me. So we spoke about limits. So now I want to look at one-sided limits. When I speak about one-sided limits, remember that we've been looking at the x values coming from the left or coming from the right. We said we're looking at both if the y values are approaching a specific point. Because it's possible that the x values as x approaching that limit, sorry, at some point from the left, the y values are approaching a certain point. And when the x values is approaching x from the right, the y values are approaching a different point. So it is possible that that is the case. So for that, that's why we have these one-sided limits. So the one-sided limits, let's maybe define it first. So as you can see from here, we have this negative here as an exponent, but it's not an exponent. This is just a notation. So here, because the previous example, we didn't have this negative, because we're looking at the limits both from the left and both from the right. So that's why we didn't have an exponent here. But in this case, we put this negative here as an exponent, but this is a notation. This is not -1, or this is not any negative point. We just put this minus here to show that we're talking about the limit from the left. And we get to say that the limit, we call this the left-hand limit. So we say that the limit from the left of f of x as x approaching a from the left is equals to L. So meaning we're only looking at the x values approaching a from the left, meaning looking at those x values that are less than a. I hope I'm making sense. And same thing as the right-hand limit, we're looking at the x values that are approaching a from the right, meaning we look at the x values that are greater than a and keep on reducing them approaching a, and look at how does the y value approach the value L, or how does the y values behave. So for that, we can, the issue of limits, this is also what we call the one-sided limits. So for us to have said that the limit exists, or for us to say that the limit is equals to L, this is when the left-hand side limit is equals to this L, and the right-hand limit also approaches L. So meaning if you take the values of x that are smaller than a and keep on increasing them approaching a, meaning the x values approaching a from the left, the y values are also approaching L. And again, if you look at the values of x that are greater than a and keep on reducing them to approach a, or meaning x approaching a, the x values approaching a from the right, and the y values are also approaching L. If both the left-hand side limit is L and the right-hand limit is also equals to L, this is when we say that the limit of f of x as x approaches a is equals to L. Otherwise, if this left-hand limit was going to L1 and the right-hand side limit was going to L2, whereby L1 and L2 are not the same, therefore, we'll say that the limit does not exist. I hope I'm making sense. Maybe let's take this piecewise function. So we say that this h of x, whenever x is less than 0, meaning from -infinity until 0, the function will be defined by cos x. When x is equals to 0, meaning on the region, the y value will be half. And on the domain of from 0 to infinity, the function will be defined by this straight line y is equals to x. So from this example, we are asked to sketch this function, then look at the limit as x approaches 0 from the left, the limit as x approaches 0 from the right of this h of x, then from there conclude what is the limit of h of x as x approaches 0. And again, look at what is h of 0. So sketching the function is quite easy. So remember we said for the values of x less than 0, meaning for all those negative x values, meaning from -infinity until 0, we use the function is defined by the function of cos x. As you can see, the function of cos x, this will be a function of cos x. We remember the function is not defined at when x is 0. We only say the function is defined by this for x value is less than 0. And when x is equal to 0, the function is half. So meaning when x is 0, as you can see, this is the this blue dot here, which is half. So meaning the function is half. And again, if you look at the values of x being greater than 0, meaning the domain, when the x values are positive, the function is defined by a straight line, y is equals to x. And as you can see, there it is. So meaning this is our piecewise function. So for x being negative, the function is defined by cos x. When x is 0, the function is defined by half. When x is positive, the function is defined by a straight line going through the origin. But it's not defined here. So remember that you said this open circle here, as you said the function is not defined at that point, then the dot line is to say that at the specific point, here's the y value. So this is our sketch. Now we have to look at our limits. So if we look at, now we are asked to look at the x values approaching 0 from the left, what are the y values approaching? So if you look at this function, as the x values are approaching 0 from the left, remember that here, the 0 point is here. So when the x values are approaching 0, the y values can you agree that the y values are increasing and the y value is approaching 1? I hope that makes sense. So you can say that this will be equals to 1. And if you look at the x value approaching 0 from the right, meaning we look at the values that are greater than 0, so we get to reduce them, approach 0. So the y values are also decreasing, they're approaching 0. So it means that now we can say that the function approaching 0 from the right is equals to 1, is equals to 0. I hope that makes sense. And again, remember that the function is defined. We said when x is 0 is equals to half. So meaning h of 0 is equals to 1 over 2, because this is, we are told that when x is 0, the function h will be given by half. So this is what we get. But now, as we said, the limit as x approaches 0 of h of x is equals to 1, because you can see the y values are increasing, they're approaching 1. And here, when the values of x are approaching 0 from the right, the function is approaching 0. Like we said here, when you're approaching 0 from coming from the right, the y values are decreasing, they're approaching 0. So for this, because the limit from the left and the limit from the right are not equal, so for that we say that the limit does not exist, because the y values coming from the left and coming from the right, they are not approaching the same point. I hope that makes sense. So this is when we say the limit does not exist, because for the limit to exist, or for you to say the limit is 1, or the limit is half, or the limit is 3, or -10, it means that the limit from the left and the limit from the right should be going to the very same point. I hope that makes sense. Now when I look at infinite limits, so this is where we define the asymptotes that you normally know. For example, if you look at the function of y, the function of y is equals to 10x. We know that this function at 90 degrees, if we use the degrees, the function is not defined. So the function looks okay. So the function goes to positive infinity. And here at 1, then we have 180. Then we're going to have 270. So we know that at 270, the function is not defined as well. So we know that here the function will be looking something like this. So basically, when we talk about infinite limits, as you can see, the function goes to infinity as x approaching 90 degrees. So basically, that's the whole idea that you talk when we talk about infinite limits. Now, let's look at, for example, let's look at the function 1 over x squared, and we want to see if the limit exists. So if you look at the x value approaching 0, starting from the left and starting from the right, when you substitute these x values into 1 over x squared, as you can see, the values of x, they're just busy increasing, they're not coming to a specific point. And for that, this is when we say, as you can see, we're coming from the left and we're coming from the right, and the values of y are just busy increasing, going up, they're not going to a specific point. So for that, we get to say that the limit of 1 over x squared as x approaches 0 is equal to infinity. Remember that infinity is not a specific number. We just say that the number keeps on growing and growing and growing. So he also say that when the x value is approaching 0, coming from the right, the y values keeps on increasing. And look at the x values approaching 0 from the left, the y values keeps on increasing. So because now coming from the left and coming from the right, the values of y, they keep on increasing, going to infinity. So we said that the limit of 1 over x squared as x approaches 0 is infinity. I hope that makes sense. So if you put that into a definition, we say that let f of x be a function defined on both sides of a, meaning coming from the left and coming from the right. We don't really care what happens at a. Then the limit of f of x as x approaches a is infinity. This means that the values of f of x, meaning the values of y, becomes larger and larger when you take the values of x to be closer and closer to a, but not equals to a. So this is when we say that the limit is infinity. I hope that makes sense. So another notation we say that f of x goes to infinity as x approaches a. There's one way of looking at it. And again, remember that infinity is not a number, it's just an expression to say that the number becomes bigger and bigger and bigger. I hope that makes sense. So we say that f of x becomes infinite as x approaches a, or f of x is increasing without bound, meaning it just keeps on increasing and increasing as x approaches a. So this is when we say that the limit is infinity. And again, the function can go to negative infinity. So we say that let f be a function defined on both sides of a. So except at a, then the limit of f of x as x approaches a is minus infinity. This means that f of x can be made to be large, negative, or becomes very small. Remember that when I say small, I'm not talking about 0. Remember that -2 is less than 0. -5 is less than -1. -100 is less than -1. Those numbers are smaller and smaller. So basically what we are saying here, we say that the y values, the limit of the y values as x approaches a is negative infinity. Let's take an example. Or we can say that the y values keep on decreasing when x approaches a. If you look at an example, we can take -1 over x squared. So this is how the function looks like. As you can see, when x is approaching 0, coming from the left, sorry, coming from the right and coming from the left, the y values keep on decreasing without bound. So it means that these function, these values, they are going to, we can say that they become very large negative. So you can say the function goes to negative infinity. I hope that makes sense. So this is what we mean when you say that the function goes to negative infinity. So we have, and again, for one-sided limit, we can say that coming from the left, the function is, we can have a definition of say the x approaching a from the left, the function goes to positive infinity, or coming the x approaching a from the left, from the left, f of x goes to negative infinity, and same thing as the right-hand side limit. They can also be infinity or negative infinity. Remember that x approaching a with this exponent negative here, it means that we consider the values of x that are less than, meaning if you look at, if a is somewhere here, so x approaching a from the left, it means that we're coming from, we can't really say that, but you can think of it, if it's confusing you, think of it as coming from the negative side. I mean, when you come from the negative side, it means that we're coming from the left. This is what x approaching a from the left means. And x approaching a plus, you can think of it. I'm not saying it necessarily means coming from the right, but think if it's confusing you, think of it as values of x that are greater than a, meaning we're coming from the positive side. This is when you're coming from the right. These are very important notation when it comes to these limits. So we are asked to evaluate, we have a hyperbola here, 1 over x, and we are asked to evaluate the limit coming from the left and also coming from the right. This is the hyperbola. So as you can see, when x is approaching 0 from the right, the function goes to positive infinity. I hope you can see that. And when x is approaching 0 from the left, the function keeps going down, or the function becomes smaller and smaller. The y values are getting smaller and remember, these are the y values. So it means that the function is going to minus infinity. I hope this makes sense. We have this function here, cosec. So this is another notation for cosec, but this C as C basically is just the short for cosec x. Remember that cosec x, we said this is same thing as 1 over sin x. This is the same as 1 over sin x. So if you remember the function of sine, it looks something like that. It goes between 1 and -1. So it means the function of cosec, remember that these are inversely proportional. So it means that when here the function is 0, it means that for the cosec, we cannot substitute 0 because we're going to have undefined. So it means that the function has to look, it has to be 1 here. As you can see here, we are approaching 1. These are inversely proportional, meaning when this one, when the function of sine increases, the function of cosec is to be decreasing. And when the function of sine is decreasing, the function of cosec is to be, so we're going to have something like this. Because here we have 0, it means we're going to be having an asymptote for the function of cosec. And same thing here. So the function is going to look, something like this. I hope you get an idea. Let me just draw the function. So this is how the function looks like. So as you can see here, pi, remember that pi is 3.14 something something. So using the radian measure, so it means that here, where sine is supposed to be 0, we have an asymptote here. So if you look at x approaching pi, which is somewhere here 3.14 something something, when x approaching 3.14 from the left, the function goes to positive infinity. And when we look at x approaching pi, which is somewhere here, coming from the right, the function goes to negative infinity. So coming from the left, the function goes up, meaning the function is going to, because it will never touch this line. It's an asymptote, it goes to positive infinity. And when you approaching from the right, when you're coming from the right, the function keeps going down, meaning it goes to negative infinity because you will never touch the asymptote. I hope that makes sense. We are running out of time. We have this function here. We have this function 2x all over x minus 3, and we ask you to look at the limit coming from the left and coming from the right. Please know that as much as look at the numerator, we can substitute 3 in the numerator. 2 times 3 gives us 6. But in the denominator, we cannot substitute 3 because 3 minus 3 will give us and it will give us 0, whereby because now x minus 3 is on the denominator, will end up having undefined. So meaning we cannot substitute 3. Hope that makes sense. So for that, it means that if we, for example, you take 3.01, meaning we're looking, remember that we're looking for the x approaching 3. So if we substitute those x values in the denominator, those values will be approaching 6 because 2 times 3 is 6. So meaning those x values, either they are bigger than 3 or less than 3, but substituting those x values in the numerators, all those will be approaching 6. But in looking at the denominator, those will be approaching 0. And for that, it means that we can't look at when x is 3. So, but otherwise, if we get to draw the table, for instance, if we take 3.01 and we substitute it here, 2 times 3.01, we get 6.02, then 3.01 minus 3, we get 0.01. And for that, 6.01 divided by 0.01, we get 602. So for that, it means that the numbers, when you come from the right, meaning for the values of x that are greater than 3, the function will be going to positive infinity. I hope that makes sense. And when we get x, the values of x approaching 3 coming from the left, the function, those values will be negative, because remember that 3 is positive. So even if we get 2.999, which is the value that is less than 3, so we're approaching 3 coming from the left, the 2x will still be positive because 2.99 times 2, those are both positive. So the answer will be positive. But when we look at the denominator here, 2.99, which is the number that is less than 3. So that number minus 3 means we get a negative number. So for that, it means that we'll be going to negative infinity. So this is how the function looks like. So as you can see, coming from the left, the function goes to negative infinity, and coming from the right, the function goes to positive infinity. I hope that makes sense. So that's what you call vertical asymptotes. So whenever if the function x approaching a, the y values goes to infinity, either coming from the left or coming from the right, those dotted lines, we get to call them the vertical asymptotes. I hope that makes sense. Remember that for you to have a vertical asymptote, even if coming from the left, you go to positive infinity, and coming from the left, so you only need one. Even if coming from the left alone, you go to positive infinity, we have an asymptote there. So it doesn't mean that you need all of them or at least 2 of them. As you've seen from with some function, the function can look, hyperbola can look something like this. So coming from the left, the function goes to negative infinity, it means we have asymptote there. I hope that makes sense. I'll stop here. Any questions? If we don't have any questions, then we can stop here. Yeah, then if you don't have any questions, then we can stop here. In case you're going through the video or going through the slides and you have questions, you can just email me as to, which is K Sebogodi, SEBOGODI at uj.ac.za. So this is my email address. In case you have any question or any question for that matter, you can just email me on this email address. Then, yeah, we'll talk. I normally give out my numbers, but my partner told me that I'm very beautiful, so I should stop doing that. Ladies and gentlemen, I'll stop here. Thank you.